In this lesson, we're going to review two sections. The first section is relations and functions. A relation is an ordered pair, an x value and a y value. So a relation is a set of ordered pairs. When we have a relation or a function, we want to establish a domain and range. The domain is the x values or the input. The range is the y values or the output. So here's a set of data. The x values are 1, 2, 3, 4, 5. That's the input, the x values. So the domain is 1, 2, 3, 4, 5. The y values are 11, 12, 13, 13, 13. Those are the outputs. So the range is 11, 12, 13. If something repeats, we don't need to write it more than once. When we look at a specific scenario, we want to figure out what's a reasonable domain and range. So here's a situation. A hose fills a 10,000-gallon swimming pool at a rate of 10 gallons per minute. The water in the pool depends on how many minutes have passed. So the dependent variable, or the y values, are going to be the gallons in the pool. The independent variable is the minutes, so that's the x values, the input. The minutes determine how many gallons are in the pool. So a reasonable domain is 0 minutes to the time it takes to fill the pool. Negative minutes is not reasonable, so that's a constraint on the domain. The range represents the gallons in the pool, and again, you can't have negative gallons in the pool, and the pool holds 10,000 gallons. So a reasonable range is 0 to 10,000 gallons. Here's another situation. A restaurant needs to order chairs for its tables. One table can accommodate 4 chairs. So the number of chairs depends on how many tables there are. So the chairs are the dependent variable, or the y value. The tables will determine how many chairs we have. So tables is our x value. So now a reasonable domain, again, you can't have negative tables, but you also can't have half a table. So our domain is 0 tables to the number of tables needed, but a constraint is it has to be a whole number. The range represents the number of chairs. We won't have negative chairs or a half a chair, but we'll have 4 chairs per table. So our range is all the multiples of 4 from 0 to 4 times however many tables we have. So that's finding a reasonable domain and range. Now, another quality of relations or functions are if it is continuous or discrete. Continuous means it includes all real numbers, so that could be fractions and decimals and so forth. Discrete means we only have whole numbers or integers. So in our pool problem, we had minutes. Well, you can have a half a minute. You can say the pool's been filling for 3.5 minutes. And you can have a fraction of a gallon. You could say it has 42 3/4 gallons. So on a graph, we would connect everything up because it includes all the possible values. So that's continuous. In our table and chair problem, you can't have a half a table or a half a chair. You can only have whole numbers. So all the values in between aren't connected, so we end up with dots. So that's a discrete function. Now, the difference between a relation and a function is any set of ordered pairs, but in a function, in that set of ordered pairs, each input has exactly one output. So for each x value, there's only one y value. So here is a set of ordered pairs, 3, 9, 4, 16, 5, 25, -3, 9. Each x value appears only once. So we see a 3, but we don't see any other 3. Now, we see that the 9 is the y value. We do have 2 9s, but that doesn't matter. In a function, we only want to see the x value one time. And so for each number, 3, 4, 5, and -3, they only appear once. So yes, that is a function. Now, in the set of ordered pairs, 3, 7, 4, 8, 5, 9, 4, 0, 6, 0, we see that the 4 appears twice. In the first instance, the 4 is associated with an 8. In the second instance, the 4 is associated with a 0. So that input has two different outputs. So that is not a function. So in a function, the y value can appear more than once, but the x value can only appear once. Now we have another quality for a function, and that's if it's a one-to-one function. In a one-to-one function, then we only want to see the y value appear once. So no two elements in the domain map to the same element in the range. So when we look at our function that we looked at just a minute ago, we saw it was a function. However, there were two y values that were the same. So that is not a one-to-one function. On the other hand, something like this, the 8 only has one value associated with that, and that's the 3. The 10 only has the 1. The 12 only has the 4, and so forth. Okay, each x value only goes to one y value, so that is a function, and each y value is associated with only one x value, so that is a one-to-one function. Okay, so that's 3.1. Now, 3.2 is linear functions. So in other words, we're looking at functions that if you graph them, they make a line. We write things in function notation for a number of reasons. Function notation is, instead of putting y equals, we put f of x equals. So there's an equation in function notation, f of x equals 3x plus 4. F of x equals is the same as y equals. But with f of x, now there's things that we can do and ways that we compare other functions. So when I have f of x equals 3x plus 4, whatever I put in for the x in the f of x, then I'm going to put that same value in for the x in the formula part. So whatever we put in the parentheses, we're just putting that into the function where the variable is. So if I had f of something equals 3 times something plus 4, if I take a 2 and put it into f of 2, then I'm going to put that 2 also in for the x. So that's using the function notation. So what is the value of g of x equals 5x plus 1 when x equals 3? Can you figure that out? When we put the 3 in for the x, we put it in for the other x, so g of 3 equals 5 times 3 plus 1, or 15 plus 1, which is 16. So g of 3 equals 16. Now, we also want to be able to write a function when we're given data. So here's some data, and we want to write a function to determine the cost for any number of bracelets. So we can see one bracelet costs $17, two bracelets cost $32, and so forth. So we want a function to represent this. Now, we can see for every change in x, we're only going up 1. The y values, the cost, is going up by 15 every time. 17 plus 15 is 32. 32 plus 15 is 47, and so forth. So the constant rate of change, the change in y over the change in x, 15 over 1, is 15. So when we look at a linear function, we're looking at that y equals mx plus b. M is the rate of change. So we're going to put the 15 in for the m. Now, we want to represent the x and the f of x as x and y. So we can pick any point. Picking 117 is easy because 1 is easy to work with, but we could pick any point and it would work the same. So we're trying to solve for b. So we're putting the 1 in for the x and the 17 in for the y, or the f of x. So 17 equals 15 times 1 plus b. 15 was the rate of change, 1 was the x value, 17 was the y value. So now 15 times 1 is 15, subtract 15 from both sides, and we get b equals 2. So now we can rewrite our function. We have the m is the 15 and the b is the 2. So f of x equals 15 plus 2. So that's how we can write a function. There's our answer. 15, or f of x equals 15x plus 2. We saw the rate of change was the 15, so that went for 15x. The 2 is the y-intercept. The y-intercept is the 0 term. We don't have that in this chart, but if I backed up 1 to get to the 0 term, then I'd back up 15. 17 minus 15 is 2, and there's our y-intercept. So there's our 2 lessons for today. Now you're ready to do the problems that are assigned.